হ্যালো।
হ্যাঁ স্যার।
হ্যালো।
হ্যালো
হ্যাঁ। So what happened?
স্যার, আমি অন করে বসেছিলাম কিন্তু মানে
হুম,
এই হচ্ছিল আর কি।
আচ্ছা। কি হচ্ছিল না?
আমি অন করে বসেছিলাম কিন্তু মানে আপনি অন করতে বললেন, মেসেজ দেখলাম, তখন তার আগে থেকে অন করে বসে আছি
হুম,
কিন্তু।
হ্যাঁ। অন মানে ওই ইমেলের যে লিঙ্কটা, ডিড ইউ
হ্যাঁ,
ইউজ দ্যাট? নো।
হ্যাঁ, আমি এই গুগল ক্যালেন্ডারে নোটিফিকেশান থেকে আমি অন করেছিলাম ওখান থেকে।
হ্যাঁ, 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 আচ্ছা। তবে কি জানি না, কিছু প্রোগ্রামে প্রবলেম কিছু হচ্ছিল সেটা। ওকে। সো সো যেটা what we'll do is, uh, so you have done a little bit of
এসিপি একটু।
SEQ2 from the Varnowitz paper, right?
হুম।
So what you are now somewhat familiar with is this sister algebra.
আবার এসিকিউ টু।
Huh? Huh?
সিস্টার অ্যালজেব্রা আবার এসিকিউ টু।
Huh? This one.
হুম।
এটা নোটেশনটা রাইট, ওই the one generated by two elements alpha and beta satisfying all these relations and all. And and you would have seen that hop
কো
structure
মাল্টিপ্লিকেশন।
etc. on this co-multiplication, co-unit and
কো ইনভার্স।
anti-co and so on. So this is a non-commutative version of what happens for a compact group, right? That also, I mean, I've not gone into it in great detail, but you have seen to some extent that if you have a compact group G, then CG has a similar kind of structure. So this is a sister algebra first of all, and then you have this map, and then you have a co-unit there and an antipode. So this Hopf algebra that you have seen, Hopf sister algebra, that's an analog of this situation of a compact group. Okay, so what we'll do is look at the other picture. So what happens is, if when you have a compact Lie group, you also have its Lie algebra, right? Okay. So for example, you have this group SU2, so then you have this Lie algebra SU2, and here this CSUQ2 together with that all that.
হ্যালো স্যার। স্যার হ্যালো
So
স্যার
so looking
স্যার
yeah.
এই জায়গা এই এসিকিউ টু ডিফরমেশন এই জায়গাটা আরেকবার বলবেন মানে এই
হ্যাঁ,
সময়টা
so deformation কথাটাই we have not it has not been defined, it has not been made precise. What I'm saying is roughly you can see that the SuQ2 when you're studying in Varanovich, that's close to the group SU2. So SU2 you have this group operation,
হ্যাঁ
you have this inversion, okay, and also you have this identity. So now when you study this sister algebra, so here you are essentially studying the non-commutative version of this structure.
SU2
So you have this sister algebra, you have a co-multiplication map from this, you have a co-unit from A to C, and you have antipode which is not exactly from A but slightly smaller part of A to A naught, satisfying those half algebra conditions. So these are analogs of the corresponding maps for SU2 groups. So for example, for SU2 group, you have this would give you the corresponding map here. If A is similarly epsilon and so on. So this is similar to this picture, SuQ2, the description of SuQ2 that you have studied. That is taking this picture and then instead of looking at this abelian commutative sister algebra, you are looking at something non-commutative, and then you are looking for a similar structure, or the structure you are given that is similar to this structure here. So there what you have is A is a unital sister algebra. In addition, you have these maps delta, epsilon, s, etc., which make it, roughly speaking, of sister algebra. And then as you go further in that paper by Varanovich, or let's say that note by Netviev to say, so you'll study representations of this object and so on. So
স্যার কিছু লিখছেন
and okay.
Okay.
So now what I'm saying is what we'll do is look at the Lie algebra SU2, small SU2. So this is the Lie algebra of this group. Now we'll do a similar thing here. Similar meaning similar not literally, but similar in the sense that we'll just disturb this structure a little bit and then arrive at something, some object which we'll call the Q deformation of SU2. So this would be at the Lie algebra level, and then from here we'll see that there is a passage to the sister algebra that you are studying. Okay.
Oh.
And also, so here when you are studying the sister algebra, among other things, one thing you have looked at are, let's say, representations of this sister algebra. Okay. So there are two kinds of representations in the picture. So right now I'm talking about representation of the sister algebra.
Okay.
In Voroniz's paper, what you will see as representations are representation of the quantum group. That's slightly different. That understand what I'm saying. So that condition, if you remember, something like this, right? So that their representation refers to representation of the quantum group structure or the Hopf structure. So that is one representation that's around us, and it's a sister algebra, so we can talk about sister algebra representations, and which you have already looked at now. Those irreducibles are parameterized by the unit circle. So there are two families, right? Infinite dimensional ones, which all live on L small L2 of n, and then another family which are all one-dimensional sister algebra representations, right?
Yes.
So what we'll try and see is, so when we come from this side and arrive at this sister algebra, we'll see that those sister algebra representations have a will have some geometric meaning. So we'll try to see that towards the end. But to begin with, our goal is to just start from this Lie algebra and then take it forward. Eventually, define deformation of the structure. Okay.
Okay. So I'll just start with the definition. So what is a Lie algebra? So a Lie algebra G over a field F. So F for us typically would be C.
Either R or C.
Okay.
But the definition makes sense for a field F. Can be a field. So when do we say it's a Lie algebra? So it has to be a vector space, of course. And it has to have a product. Okay, so product means an operation that takes you from G cross G to G. Okay. Did you say something?
No, sir.
No. So the product for Lie algebra, the standard convention is to use this kind of notation. So A, like for a ring, etc., the product you denote by just writing AB. So here the standard convention is to use this notation. Okay. So it has to be a vector space. It has to have a product such that the following following two conditions are satisfied. So what are the two conditions? One is that so it's not commutative, but it's anti-commutative, right? Product of AB plus product of BA, that's 0. And it satisfies another condition which is called the Jacobi's identity, which says that so once you have a vector space with a product which satisfies these two conditions, then Lie algebra. So most examples we'll see, for us in fact all examples essentially will be something sitting inside some matrix algebra, either MNC or MNR. Okay, and in those examples, the product would typically be given by this. Okay. So that's one of the reasons this notation is used. But you have to be alert that in a Lie algebra you just have this product. So in a Lie algebra there's nothing called AB as long as you are using this notation, right? So when you are in a Lie algebra, you cannot always write this because there's no other operation.
Yes.
Right? So example, so let's say we take G to be R, vector space to be, the field to be R also. So real vector space, we take R itself and we define so then trivially both these identities are satisfied. Then you can take, let's say, all upper triangular matrices, 2 cross 2 upper triangular matrices. And then you define this to be, so G is sitting inside M2C, so their matrix product makes sense. So if you take 2 upper triangular matrices, if you compute this, you see that this is again upper triangular, so you'll be back to G. And so this is a verification, and for each of these examples, the verification we should do that this is in fact an example. And now we can, so there's nothing special about 2 here, so you can take and in fact okay, the operation remains the same. The matrix, the commutator using the matrix multiplication. So, and instead of this, if you take MNR, then you get a real Lie algebra. If you take MNC, you get a another Lie algebra. And similarly, okay, I'll just write here itself. So instead of instead of this G, if you take strictly upper triangular matrices, then you get another Lie algebra. So there also this commutator that would belong to the same class. And again, just directly compute and verify that. Then another example is the following. So take matrices of this type in 3x3 matrices of this type: 0, A, C, B, 0, 0, 0, 0, 0. And again, you define, maybe I'll use X and Y. Okay, you have to verify that the xy minus yx will again be of this form, but that you can then do. So this has a name. This has been studied quite extensively. So Heisenberg Lie algebra. And then you have same thing in higher dimension. So what is it? Instead of 3x3 now, you have okay, we'll see what 0. So instead of A, you take A1,
2,
A2, AN, then C, 0, 0, 0. So now you go B1, B2, etc. So AI, BJ, C, they are all R. So this is also, I mean, the operation remains the same, commutator. So this same name, it's just in different dimension, that's all. Then now the classical ones. So what is this? Smallest LNC. So have you studied Lie algebras?
স্যার ওই প্রথম দিকে শুরু করেছিলাম, তারপরে তো আর এগোনো হয়নি।
আচ্ছা, শুরু সেটা কি তোমায় পড়তে বলেছিলাম না আমি কিছু বলেছিলাম?
না স্যার, আমাকে পড়তে বলেছিলেন স্যার।
আচ্ছা, এটা কিরিলভ থেকে নাকি? না,
হ্যাঁ হ্যাঁ হ্যাঁ।
আচ্ছা, ঠিক আছে। Okay, so SLNC is
determinant one.
No, that is capital SLNC group.
আচ্ছা।
This is the Lie algebra. Okay.
হ্যাঁ হ্যাঁ।
So this is
স্যার ট্রেস আপডাউন হচ্ছে।
হ্যালো,
হ্যাঁ স্যার।
হ্যাঁ কি কানেকশন কেটে গেছিল?
হ্যাঁ স্যার।
হ্যাঁ হ্যাঁ, আচ্ছা, সো লি গ্রুপ অ্যান্ড লি অ্যালজেব্রা রাফলি কিভাবে রিলেটেড তোমার মনে আছে কি?
লিগ, হ্যাঁ মানে এখন গ্রুপ থেকে যে অ্যালজেব্রাটা পাওয়া যায় সবসময় তো কমপ্লেক্সের উপরে নিয়ে যেত, কমপ্লেক্স ভেক্টর স্পেসে।
না সেটা না, আমি বলছি মানে হাউ হোয়াট আর দ্য অবজেক্টস হিয়ার, লেটস সে মানে you have this Lie group and so what are the elements of the Lie algebra in terms of the group?
না স্যার।
No? Okay. So one description is the following. So you have this group G. So you look at
ম্যাট্রিক্স
one parameter subgroups. One parameter subgroups are what? So basically R থেকে G তে homomorphism, তার মানে হচ্ছে যে let's say gamma is this, then gamma set will satisfy gamma t gamma s equal to gamma t plus s, so it would be a path in G, and this would be the identity element in G. Okay, so
স্যার আপডেট হচ্ছে না,
sorry,
আপডেট হচ্ছে না।
oh so gamma would be basically a path passing through the identity element. Okay,
হ্যাঁ
এইবারে if you look at this
Gamma
would give
আসছে
you an element of the tangent space at
0 আইডেন্টি।
identity, tangent space of G at identity, ঠিক আছে?
হুম
সো এই এদের যে কালেকশন গুলো সেইগুলো they'll have the structure of a Lie algebra, সেটাই ওর Lie algebra ওই গ্রুপটার।
ওকে
সো এই জিনিসটা যদি তুমি SLNC গ্রুপের জন্য করো, you will see that you will get exactly this. SL2 এর জন্য নিয়ে ট্রাই করে দেখো, you try to find gammas. So you take the example SL2C, look at different one parameter subgroups and then look at the gamma prime zeros and see if you get exactly this.
গামা প্রাইম জিরোটা হচ্ছে ট্রেস হয়ে যাচ্ছে।
হ্যাঁ,
গামা প্রাইম জিরো এটা এটা হচ্ছে ট্রেস দিচ্ছে।
why?
স্যার
হ্যাঁ,
বলছি স্যার এই যে ট্রেস টি ইকাল টু জিরো এটা তো স্যার গামা প্রাইম ইকাল টু জিরো থেকে পাস কি?
না না, gamma prime is equal to 0 না, এটা হচ্ছে gamma prime at the point 0.
Okay.
So you are not setting anything to be equal to anything.
Okay.
So you will look at such
গামা টি
subgroups of SL2C and then take the derivative at 0.
Okay.
That will give you a matrix. So you'll see that you will get exactly the matrices here, small
Okay.
SLS. Anyway, so মানে সেটা আপনি দেখে রাখো,
হ্যাঁ স্যার দেখে রাখবো।
পরে দেখো, but for what we'll do right now, it is not important. Later on, you may need it. So right now it's not so important. So anyway, so this is an example. Okay, now next example. I mean, same thing, but you can do with, sorry, SLN R also. So here you will take matrices with real entries with the same condition. And then verify that this is also a Lie algebra, the operation is the same. So okay, then unitary small un. So what is small un? All those matrices in MMC such that so skew symmetric matrices. And then this condition together with
ট্রেস।
so এগুলো এখন just verify করতে হবে, do the verification for each example. Okay, so what we'll be concerned with is this, and later on SU2 also, but right now it will be this. So again, so what is this? This is the set of all 2 cross 2 matrices such that the trace is 0. Okay. So what is the vector space dimension of this?
Dimension 1 to 4 minus 1 3.
3. So it's easy to produce a basis, right? So for example, you take this, you take this, and
0
you take this, they will form a basis. So that again you can check. Okay, so let's denote this element by H, this one by X. This is the standard notation that is followed, so that's very good. Let's stick to that standard notation. So what we have is that this Lie algebra is just the span of
H, X,
and Y. And another thing that you can easily verify is that so the product here is the commutator, right?
Yes.
In this Lie algebra, because if you take the matrix product, you will get out of this space SLPC. So what is this commutator?
H, X,
This
2X.
And this is H. So H, X and Y, they satisfy this So these relations are going to be crucial. Okay, now exercise. Let G naught be so. So algebraically you can make sense of this object. So the Lie algebra generated by 3 elements satisfying these relations. Then it has to be the same as SL to C. So just think about this problem. First, you have to. So there are two parts. One is you have to make sense of this, right? That there is a Lie algebra. So here I have just stated that let G not be such and such object. Lie algebra generated by 3 elements satisfying these relations. But that there is such a thing that you have to convince yourself. So just think about that a little bit. And then the second part is that once you make sense of such an object, that Lie algebra has to be isomorphic to SL to C. So the second part, once you have G naught, what you have to do is you have to since H, X and Y satisfy the same relations, you will get a map that sends H naught to H, X naught to X and Y naught to Y. So SL to C would be a homomorphic image of G naught, and then you just compute the kernel and show that the kernel is 0. Then you will get an isomorphism. So try to work it out. Okay. So now what do we have? We have a Lie algebra. Okay. Now what is a representation of a Lie algebra? A representation of a Lie algebra on a vector space V. So what is it? That would be a map phi from the G to linear operators on V. And now you will impose some condition on phi. So what are the conditions that you are going to impose?
Condition that two conditions, one Jacobian identity and another is the antisymmetry.
No, I mean that is in the definition of a Lie algebra. But once you have this Lie algebra, what you have is this product. here, right?
Yes.
So now you want that thing to be preserved. So what you demand is one that and
Multiplication. Right.
so pi of
xy equal
product
pi
of
x
2
pi. Okay.
equal to, okay, now what?
Pi of x into pi of y.
No. So here the definition of representation would be that this is, you don't demand this to be this. Okay?
Okay. Pi y minus pi x. Oh.
So on LV you always have the usual product available. Okay? And there if you take the commutator as your product, then LV becomes a Lie algebra. So basically LV together with is a Lie algebra. So a representation is basically a homomorphism from G to this Lie algebra. Okay?
Yes.
So that's the definition of representation of a Lie algebra. Okay. So now let us take a natural number. Let us take a vector space of dimension m plus 1, and let's say this is a basis. Okay. Now we want to define a representation of this on. So I'll just write down the operators, but you verify. Okay, so this is for all k between 0 and m. I mean, right now I'm just writing down, and it would look like, I mean, out of nowhere this is coming out, but we'll slowly see that these are actually natural. This is almost forced, so, but that will come gradually. Right now we just want some ready-made examples of representations. So for k, kept with some coefficient, and if k is 0, then it takes it to 0. And okay, switch. And this is for k between 0 and m minus 1, and it is 0 if k is m. So it's the other shift, right shift, with coefficient m. So what is going on? So these are, let's say, v0, v1, v2, vm minus 1 and
Okay.
vm. So now what is x doing to this?
X doing left shift.
Right, x is bringing each one to, and then this one is being taken to 0. And what is y doing?
Y
Y
doing
is
right shift.
right shift. There's some coefficient, but other than that, it's this. And each vi is an eigenvector for h by h. Okay. So that this is a representation that you verify. Okay, so that computation I'm not getting into. That is just computing those relations. Right. So what you have to check is ym. So this we know that I mean in SL2C this commutator inside, that's nothing but
xy minus y.
but we have this relation, right?
That
this
is
actually the
A.
element A. So what you have to verify is that
Pi m is equal to pi m x and pi m y minus.
And so on. So there will be a few other things that you have to verify. So I'm just leaving this part. Some such relation. To verify. Now, when you have a representation, then the next thing that you start talking about is whether it has any invariant subspace. Right?
Yes.
That we have done for sister algebra also. So here also, whenever you talk about representations, you talk about invariant subspaces, you talk about irreducibility. So when is a representation called irreducible? If there is no proper non-trivial invariant subspace. Right? Okay. So let's verify whether this is irreducible or not. So let's say W is an invariant subspace. Okay? Okay. Now also non-trivial, because if W is 0, then it's fine. I mean 0 is an invariant subspace always. So let's assume that W is a non-trivial invariant subspace. That means there would be one such vector in W
which is not 0.
Okay. So now this is non-zero means at least some of the coefficients are non-zero, right? So basically, how will this look like then? It would look like if we just discard the zero coefficients, terms with zero coefficients. So it would look like and we can arrange so that right?
Yeah.
Okay. this is, let's call this small w. Okay, now if, since W is an invariant subspace, that means this. Acha. Now you look at this vector.
Yes,
How does it look like?
Pi mx of W, that is j j1 minus 1 and j2 minus 2. C j1 v j1 minus 1, that, like that.
Right?
Yes.
And if j1 happens to be 0, then this term would be missing. It would become 0. Okay. Now you apply pi mx again. So what you can do is you can eventually reach v naught.
Yes.
Right? If you just apply, let's say, pi naught x to the power jr.
Yes.
Then you will get v naught with some coefficient.
Yes.
So just check that that coefficient is non-zero.
Okay.
That coefficient would be non-zero. That will follow if you just look at the coefficients for that you get when you apply pi mx. So ultimately what you would get is that v0 is in your invariant subspace.
Now
right.
we applied pi m y.
Y, right. So then what you get is
v0 to vm all belongs to that.
All. And that means that W is equal to, in fact, Vm.
Yes.
So in fact this is an irreducible representation. Okay.
Yes.
Okay. So now what we have is for each m in n, irreducible representation of dimension m plus 1. Okay. So now next we'll try to go in the other direction. So we'll show that any finite dimensional irreducible representation of SL2C
is of this form.
Is of this form. Okay. So for that first, let's do the following. So suppose pi is a representation of SL2C on V, and let's say V so this is a okay. So assume this, then either pi x v is 0, and when I'm saying this, I'm assuming that this is non-zero. When you say eigenvector, you basically exclude 0, because otherwise 0 would be eigenvector everything. So either pi x v is going to be 0, or xv is eigenvector of phi h with eigenvalue lambda plus 2. So why is this? This should follow just from the relations, because hx is 2x, right?
Yes.
So if pi is a representation, then pi of, okay, first of all, this is going to be pi of 2x by linearity. This is pi of 2 of twice pi x. But if, since pi is a representation, this is going to be pi h pi x minus pi x pi h. So you have equality of these two, right?
Yes.
Now apply this to the vector v. Then what do you have? Twice pi x v equal to pi h pi x v minus pi x
pi is v.
pi h v, which is lambda times v, because v
Eigenvector.
is eigenvector corresponding to eigenvalue lambda. So which means that if you just change size, etc., pi h
pi x v equal to
this
lambda plus 2 pi
equal to, right, lambda plus 2 pi x v. So now the conclusion follows. Either this is the zero vector, or if it's not the zero vector, then this is eigenvector corresponding to eigenvalue lambda plus 2. So this is a direct consequence of the relation. Right? There's nothing else involved here. Okay. So now we'll try to prove the converse. So this is this statement we'll use. Okay. So now let's start with a representation and finite dimensional representation. So let's start with this. Okay. So now, where do we start?
Sir?
Yes. Where do we start?
Taking from a eigenvector from pi, non-zero eigenvector of pi is.
So corresponding to some eigenvalue. So just call that. It doesn't matter what lambda is, whatever that corresponding eigenvalue is denoted by lambda.
Now apply pi x until pi x v and until it goes to 0. Pi x v, pi x 2 v.
Okay, now the next one, what is it?
Pi x v.
So here just a bit of warning. This v. So this is not sometimes we may just like may not be alert and just write this. Usually in an algebra these two would be the same, but here
it is not.
this is not an element of the Lie algebra necessarily, so we cannot write that. So this, whereas pi x, once you are in LV, this makes sense. You can multiply. Okay, so this then and so on. So look at this. So this is going to be eigenvector corresponding to
Lambda plus 2,
lambda plus 2, lambda plus
4,
4,
some,
lambda plus 6, and so on, right?
yes.
And
Somehow it is 0.
And unless one of them is 0.
Mhm.
Once one of them is 0, the subsequent ones are all zeros.
Yes.
Okay. And the one that we started with, that is non-zero.
Mhm.
Okay. Now, it cannot be the case that all of them are non-zero, right?
Yes.
Because so if all of them here are non-zero, then you will have more than m plus 1 independent vectors, because they are eigenvectors corresponding to distinct eigenvalues. They are independent.
Yes.
So already in this list, all of them cannot be non-zero. So there is one of them would be 0. So now look at the least one. So so let's say
not equal to 0.
so so the first time it will be 0 at some stage. So in that case, you look at this. So this is eigenvector corresponding to eigenvalue something. Let's say lambda prime, or if you want to, I think original lambda will not matter. So let's write lambda prime. Okay. So let's call this W naught. Now
we apply pi y,
right. So
and
pi y j W naught u.
and until it goes to 0, and then this is the basis.
So okay. So you can see how the argument is going to go, right? So instead of, again I'll just skip the computation. So what so if you complete the argument, do the computation and complete the argument, what we'll get now is that pi h wj equal to
lambda dash minus 2j wj. Yes.
and then pi x wj is so if you do the computation, you will get exactly this, but verify it so that it's I'm making any mistake, you can detect that. So this is for 1 and 0 if j is 0, and by y wj, that's of course the way you have defined it is just wj plus 1 if j is here, and then 0 if. Now if you compare it with the earlier one, this is not exactly that, right?
Yes.
The coefficients are different.
Yes.
Okay.
Hmm.
Okay. Now first thing is, okay, so in fact before even comparing it with that representation, we need to settle one more thing. So here at this stage, show that lambda prime has to be equal to, in fact, m. Okay.
Lambda prime. Okay.
And for that, I'll just tell you what exactly to do for that. You use so this is this, right?
Yes.
And this is going to be pi x pi y minus
Pi y
pi
by
y
x.
pi x. So evaluate on
W0.
the one extreme, the topmost wm.
Okay.
So just do that, then you will see that lambda prime would become n. So we will get some equality from which we'll get this. So once you do that, then now you revise this a little bit. Then your pi h wj becomes m minus 2j wj. This is closer to the earlier representation. But when it comes to x, you are still, you have a problem, because there it was just m minus k plus 1. Now it is a product.
Okay.
Zero if j is 0, and pi y wj is wj plus 1. There is no change here. So this is not exactly the earlier one. But the point is that now you can make a change of basis so that so now you can make a change of basis so that it looks like the earlier pi m bm.
Okay.
So I won't write down exactly, but you just look at it, you will get it. It won't get. It's relatively straightforward. So, and that means with a change of basis you get that representation. That means this is equivalent to that representation, right? Change of basis means you are pre and post multiplying by some invertible matrix. The effect is there. So if you start by assuming that you have a so what is it that we started with?
We started with
Uh,
any representation.
Representation of dimension m plus 1, also irreducible. Irreducibility also would be required here at some stage, right?
Okay. Yes.
To get that the dimension is equal to this
M plus 1.
So starting with an irreducible representation of dimension n plus 1, you end up with the earlier one. So that family exhausts all finite dimensional irreducible representations. Okay, so I'll essentially stop here. So okay, one more remark. So since we outline this proof, so suppose now you don't assume irreducibility. So let's say phi v is a finite dimensional representation. So if you try to follow the same reasoning, what you will get is you start with some eigenvector, then you follow the same reasoning. So you will end up with some subspace which is an invariant subspace, and so that this is irreducible and this is like phi f for some m. Okay. So this is the vector space on which the representation phi acts. Now what you have done is you have got hold of this W1 such that this is an invariant subspace, and when you restrict it there, you get this one of those irreducibles. Okay. Now once you have a representation on V and an invariant subspace, what you can do is you can look at this quotient vector space. Okay. And on this quotient vector space, you can define phi 1 A. So elements here look like this, right? Or if you want to use, okay. Sorry. Yes. So you define it by phi a v plus W1, or if you want to use this notation, just the class of this. Right. So this would give you a representation of G is SL2C for us, but this is a more general statement. So this would give you a representation of representation phi 1 on
quotient W1.
Okay. Okay. Now there you can repeat the same argument. So now on V quotiented by W1, you will get W2 0, let's say Y0, that will so that the restriction of phi 1 to W2 naught, that would be irreducible. So and then W2, let define W2 by
and again quotienting.
You're transferring everything to V. So on V you had W1. Now V quotiented by W1, there you had a subspace W2 naught. So that W2 naught would basically would be of the form
W1 plus W2
W2. So that is the notation I want to use. So W2 is this entire thing. So the W2 by W1, that gives you W2 naught. Similarly, you will get W3. So W3 would be this entire thing. So basically you have a string of subspaces such that this is an irreducible module. So okay, another thing is representation and module. This terminology will use interchangeably. Sometimes one would be convenient, sometimes the other. So here we don't have to, when I say module, the corresponding map, that is, you can see from pi you are lifting it to pi 1, you would lift to the next one in the quotient space, etc. So you have a chain of subspaces, increasing subspaces, so that each one quotiented by the previous one, that gives you an irreducible representation or module of G. And since the representation that you started with is finite dimensional,
so it is a finite.
Finite string of subspaces, because every time you are increasing the dimension, strictly increasing the dimension. So you cannot have infinitely many of those. So you have a increasing chain of invariant subspaces. So that this representation of the quotients, they are irreducible. So that much we can essentially conclude from what we have done. The argument that we have used, we have to use it repeatedly, and we have to be careful that we are not leaving any gap. But basically, this is what we can prove right now. Okay. Now, what we would be interested in is whether, given any dimensional representation, whether we can write it as a direct sum of irreducible representation.
But
this is not immediate.
W2, we can't write W1 plus W2. W1 plus
no.
Hello.
Again it got disconnected. So see, to begin with, we have V. W1 was an invariant subspace. Then we got this representation on V quotiented by W1. There we got an invariant subspace W2 naught, and W2 naught would be of this form, W2 by W1.
W1, yes.
Okay, so W2, W1. Now W1 is invariant,
Yes.
W2 is invariant, but you may not have a complementary invariant subspace.
Okay.
Huh?
Okay. Yes.
So that may be a problem, and remember now we are in an algebraic setup, so we don't have this adjoint of an operator at our if you are dealing with a star algebra, for example, C-star algebra, then if in the C-star algebra case we had seen, right, if
Yes.
you have an invariant subspace, you take the projection, then 1 minus p.
Yes, it's also invariant.
So here we don't have that machinery available because
We choose different multiplication.
no, there's no star structure. There, what helps is star.
Yes.
If you go back to Hilbert space case, so what is the condition that, let's say P is a projection? So operator T leaves the range of P invariant. What is the condition?
PTP
is equal to PTP.
Yes.
Right. Now that by itself will not tell you or does not imply that you will have this. Right?
Yes.
It is not in general true. T can leave a space invariant, subspace invariant, but its complement it may not leave invariant.
Yes.
And when you are studying C-star algebra, the advantage was that instead of one single operator, we have a whole class of operators here,
Yes.
which is closed under star.
Yes. Then we
So
can
that
apply
you
a
can
star.
take star in this relation, and then the relation actually reduces to TP is equal to PP, and then we can conclude what we want to conclude.
Yes.
Okay. Now here we don't have that. We don't have star structure available to us, meaning we are just looking at representation on a vector space, right?
Yes.
So there's no inner product yet, and even if we introduce an inner product, this is a finite dimension, so we can introduce inner product, but even if we do that, there's no way to relate that to the Lie algebra that we are studying, right?
Yes.
So we cannot use that kind of machinery yet. So this showing a representation is direct sum of irreducibles, that is not immediate from what we have done. So next time we'll do that. We'll see that one can still do that. The only thing is it requires more work.
Okay.
তাহলে let me stop today.
Okay.
তুমি এইটা কমপ্লিট হয়ে গেলে আমায় বলো, বাট ইন এনি কেস নেক্সট মানডের আগে কমপ্লিট করো। সো ডিফল্ট উড বি মানডে।
একদম।
ওকে
ওকে।
আর ওই আর কি, কিছু জিজ্ঞাসা করলে মাঝে কোনো প্রশ্ন থাকলে জিজ্ঞাসা করো।
ওকে।
এন্ড মানে চেষ্টা করো ওই মডেলে কি ওখানে লিখতে, তাহলে কি হয় ম্যাথ জিনিসগুলো মানে দুটো অ্যাডভান্টেজ। ওটা হচ্ছে এক জায়গায় সব থাকে, হোয়াটসঅ্যাপে পুরোনো জিনিসগুলো কোথায় ওগুলো খুঁজে বার করার একটা মানে পেইনফুল। আর দ্বিতীয় হচ্ছে ওই মানে ইউ ক্যান ইউজ লেটেক্স, মানে তুমি লেটেক্স তুমি জানো তো একটু
জানি স্যার।
হ্যাঁ, তো ওই লেটেক্সে জাস্ট ডলারের জায়গায় এখানে ব্যাকস্ল্যাশ রাউন্ড ব্র্যাকেট ইউজ করবে এনক্রিপ্ট করার জন্য, তাহলেই ওই সিম্বলগুলো ওটা ঠিকঠাক আসবে।
ওকে।
আর ইভেন ইফ ইউ ডোন্ট ডু দ্যাট, ইভেন দেন ইটস ওকে, মানে ওখানে মোটামুটি কিছু করলে আমি ওটাকে এডিট করে সেটা কারেক্ট করে দেবো। ওখানে হলে কি হবে, এক জায়গায় থাকবে, পরে সুবিধা হবে হয়তো।
ওকে,
ঠিক আছে, তাহলে আমি আজকে এখানে থামছি।
ওকে স্যার।
ওকে।